Let's proceed to question 11, which is on the screen. It reads as follows. Campers are offered one of cereal, fried eggs, or pancakes for breakfast at a summer camp. So they got a choice of, well, they don't have a choice. I think the organizers, they give them, on one day they give them cereals, another day they give them eggs, another day they give them pancakes. So it's like that. Okay, the same kind of food is never served on 2 consecutive days. Right? So pancakes were served twice as often as cereal over the course of 2 weeks. So for 2 weeks you have these things given. Let's call them cereal, C for cereal, E for eggs, P for pancakes. All right, so you've got these things are given CEP, CEP for 14 days now. Need not be in the same thing. They need not be in the same order. But they do say that pancakes were served twice as often as cereals. So the P's occurred 2 times more than the C's. Okay, and then what else are they saying? The same kind of food is never offered on 2 consecutive days. So you don't have C and C following each other, for instance. Right? That is out. Okay, so that's all the information that is given. Now they say determine how many times fried eggs were served. Okay, so the question is, how often was E served? So you've got C is a number of times, P is a number of times, and E is a number of times. Let's call them C, E, and P. C is the number of times cereals were served, and so on. So let's do that. Oh, I've wiped out everything. So let's say that let C, E, P be the number of times cereals, eggs, and pancakes, respectively. We have to say respectively to say that these are in the same order as that, respectively. Number of times these things were served. Okay, we do know that pancakes were served twice as a number of cereals. So P occurred 2 times more than the cereals over the course of 2 weeks. So altogether, they were served on 14 days. So if you add up the number of times these things were, it's 14 days. So C plus E plus P is 14. So these were the number of times that each of these things were served. And we just got that P is equal to 2C. So you've got E plus 2C. Well, this is 2C. So therefore you have E plus 3C is 14. Because P is 2C. If I substitute, I get that. Let me make eggs the subject because they want to know how many times eggs were served. So let E be equal to 14 minus 3C. -14 3C. All right, so depending on what C is, you've got E. So Suppose you have C was not served at all. Over those 14 days. Or C was served once, or C was served twice, or C was served thrice. In each of these cases, we try to see what E is. Here you see E is 14. If C is equal to 1, E is 11. If C equals 2, E equals 8. If C equals 3, E equals 5. Now, I suggest to you that all these first three can be eliminated because you've got 14 days, you see. And if eggs are served 8 times, for instance, in 14, if you put E 8 times in a string of 14 days, see, you can put them alternatively, clamp them up together, and you will have 7 of them. But then the 8th one, it will be next to one of the others. You see, the two E's cannot be next to each other. They say here that the same kind of food cannot be served on 2 consecutive days. So if I got 14 days and I'm putting E, slotting E into those 14 days, I can't put 14 because that obviously they're all next to each other. So all these can be eliminated. And the eighth one is just about because you can put 7 on alternate days, but then the 8th one will have to be next to one of those days. So therefore E is equal to 5. Okay. So that's the answer to the question. How many times were fried eggs served? All right, so it's just a logical problem using the information that was given. Oh, I took too long to solve this. This is a very bad solution. It still comes to E equals 5. Everything is around here. At this place here, I think it's the same thing. So we put all these, and we should have say C equal to 0, 1, 2, 3, and so on. And then you get the E's, and we are saying, oh, there was an E equals 2 as well. You could have had E equals 2. But then that will give you P equals 8. Okay. So there was a fourth possibility, but then that will make the pancakes equal to 8, and that cannot be. So therefore, P equals 5 is the only solution. All right, so it's a good thing I looked at my prepared solution and found that there was a little bit more to be said on that problem. Okay, so we now go on to the next problem, which is question 12. So question 12 says the following. The numbers, there are 6 numbers here. 2, 3, 12, 14, 15, 20. No, 7 numbers, and 21 are arranged in 2 different sets. The product in one set is the same as the product in the other set. So what you got here, you got 2 sets here. And you got some of these numbers are pushed inside here, and the 7 numbers, and there's some of these are put inside here, maybe 5 and 2, and another 2 here. But the product of all these numbers is equal to the product of these. And they say, what is this product? So let's give a name to the product. Let n be the product. So what you have is that there's n on this side, the product is n here, the product is n here. So you have, if you multiply all 7 numbers, then you're multiplying everything from here and everything from here, but both of them are the same. So you have n squared is equal to the product of all these 7 numbers. So it's 2, I'm going to put dot 3, dot 12, dot 14, 15, 20, 21. So these are 7 numbers. So this is a square. So all the prime factors, you see, when you have a factorization of a square number, then all the, and you write it as a product of prime numbers. Every number can be written as a product of prime numbers. You will see that the exponents are all even. See? If you take any number, say a to the, say alpha, b to the beta, c to the gamma, and so on. And if this is your number, or let's make these primes, p1 to the power of a1, p2 to the power of a2. If you take any number, you can write it as a product of prime powers. All right, if you take 80, 400, make it, let's take one of the lots of factors, 420. You can write 420 as 10 times 42. Okay, they're not prime. 10 is 2 times 5. Okay, both of them are prime. This is 6 times 7. 6 is not prime. So you carry on. 2 times 3. And there it is. You've got this number is a product of prime numbers. But if you put them together, 2 occurs twice. 3, put them in ascending order. 3, 5, 7. Then you have a factorization of primes powers. You call them prime powers. And you can choose these to be of increasing order. So you can have P1 is less than P2. This is not vital, but for neatness, I'd like to start with the smallest and go. But these are exponents. And if you take any number which is like this and if you square it, you can see all the exponents are even. See? Because you can multiply by the third law of indices, you have that this all squared, and then p to the power of a1 squared is p to the power of 2a1. And 2a1 is an even number. So a square number has got even exponents. Now you got a square number here. So let's take out, take 7 out from here. 7 is the largest prime. You'll notice 7. So you got a 7 squared. But when you take 7 out, you got a 2 there. You got a 3 there. All right, you got 7 squared. And same thing with 15. That's the second largest prime. So let's take that out. That again occurs twice. We can take 5 squared, take one of those 5s out from there, and take that 5 out from there. And now the next one you have is 3. Right. It's 3, you can take it out completely, take it out completely, take it out completely. But there's a 3 here. So when you take the 3 out from here, you're left with 4. So you've got 3 to the power of 4. Because 3 was taken out completely 4 times. And then what are you left with? You're left with 2. So you got 2, 8, 16, 64. So you got 2 to the power of 6. So you can see n is equal to this. And as you can see, it's all the exponents are all even. So the number n that we're looking for is just 2 cubed. It's the square root of this. 3 squared, 5 times 7. So this is 2,520. 8 times 9 is 72, times 5 is 360. 360 times 7. So the answer to the question is 2,520. That is the product that we're looking for. The product, it was called n. All right, so that takes me to the actual, my calculation. And so there it is. You can see the last number is 2 cubed times 3 squared times 5 times 7. That's exactly what I got, which is 2,520. So let's get on to problem number 13. Problem number 13 reads as follows. In a triangle with integer side lengths, okay, so you got a triangle where the side lengths are all integers. One side is 3 times the other, while the third side is 15. All right, let's just have a look at this triangle. One side is 3 times the other, so we're going to make one side pretty long, and it's 3 times another one. Right, so if this was, if the length of this was A, then the length of this is 3A. Right? And the third side, this one is 15. So you got one unknown here, that is A. Find the largest perimeter. In other words, the perimeter is, so in other words, what is 4A plus 15? Maximum. The largest possible value of the sum of the 3 sides of this triangle. Now, there is a extremely important rule, and this is, I've noticed that this question, this fact is tested quite often, namely that the sum of 2 sides of a triangle of any triangle is always greater than the third side. Cannot even be equal, greater than the third side. This is a very important fact. In higher mathematics, this is used very often, and it's called triangular inequality, or triangle, A-N-G, triangle inequality. Because it's, you got a sum of 2 numbers is greater than the third number. So that becomes an inequality. Okay, so in this particular case here, if I ignore 15, I've got 3A plus A. Those two is greater than 15. Ignore A, you'll have 3A plus 15 is greater than A. And ignore 3A, and you have 15 plus A is greater than 3A. Sum of 2 sides, and on the right-hand side, I've got A, 15, and 3A. All right. Now, these are all inequalities. So here, we got 4A is greater than 15. So A is greater than 3,75. That's 15 over 4. And here you have, now you got 15 on this side. So you got You got well, this is always true because 3a plus 15 must be bigger than a, obviously. 3a is bigger than a. Okay, so this doesn't contribute anything. This one, you got 15 is greater than 2a. You bring the 8. So there you got 2a is less than 15. So a is less than 7,5. Because 2a is less than 15. So a is less than 15 over 2. So you want the largest possible value, and all of them are integers. So you can see this one here is crucial because a is always smaller than 7,5, and this tells you what the largest possible a is. Largest a is 7 because they all must be integers. See? So the largest a, which is less than 7,5, is 7. So therefore, we can say that the maximum perimeter this was the question. I always like to put the question somewhere so we know where we are heading. So maximum perimeter is 4 times 7 plus 15, which is 43 centimeters. Always put units. The question has the units in it. All right, so that's the answer to this question, 43. I want to check my prepared answer. There it is. You can see. Where did I get a comma? A is less than 7,57. I think that's a typo. That's a typo error. 7,5. Okay, but the answer is 43. So let's get on to the next problem. Question 14. Now here you get something which is looking rather frightening. Let me try to unpack this. Prove using induction. Now, induction is something which only some people will know. So we'll have to talk about induction. And here you got this sign here, which is not a very familiar sign. It's called sigma. And you got factorials, yeah? Factorials, you should know what factorial means. Right? N factorial is 1 times 2 times 3 all the way up to n. And this problem is involving sequences. Right? And there's a formula for the sequence. Each term in the sequence is given for different values of k. So if k equals 1, you got the first term of the sequence, a1, substitute k here. K equals 2, you got the second term of the sequence. So you got the terms of the sequence here. And you are asked to prove that, or you have to prove two things actually. You have to prove this formula, prove using induction, that, and you have to prove this formula here as well. Okay, so let's test this formula. So what do you mean by sigma? This thing here it's called sigma. The Greek S. The Greek capital S. There is a smaller, I think the small s looks like that. This is a capital S. The S actually, they use the symbol here for sum. Say S for sum. and this is a capital S. So we think of this as sum. This bottom number is, you got some symbol here. This bottom number means this is the start of the sum, R equals 1, and here the end of the sum is R equals N. So A really means you must prove that. Now, let me just explain what you mean by sum. If you say sum of n squared, for instance, where n equals 1 to 3, and so what you do is you substitute n equals 1, you have 1 squared, right? But this is a sum, so the next, you add to this, the next value of n is 2, then you add to that, the next value of n is 3, and you have to stop there because the upper symbol says this is where you stop. So when you work this thing out, is 1 plus 4 plus 9, which is 14, or 13 at least. So this rather cumbersome looking object, its value is 13. So just like that, now we need to prove this formula here. So you'll have 1 times 1 factorial when you put r equals 1, plus the next value for r is 2, 2 times 2 factorial. That's what you substitute. This is equal to when you substitute r equals 2, and so on, plus again 3 times 3 factorial. And you keep going on. Now this time you'll put dot 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 because we don't know what n is. So we'll stop at n, where r is n times n factorial. And you have to prove that this is equal to, I'm going to put it at the top here, n plus 1 factorial minus 1. So let's try test for n equals 4 maybe. It's a nice small number. So when n equals 4, you have on the left-hand side, we'll put LHS is 1 times 1 factorial. 1 factorial is 1. 2 factorial is 2. 1 times 2. 2 times 2 is 4. 3 factorial is 6. 6 times 3 is 18. 4 factorial is 24. It's a 6 times 4, because 4 times 3 factorial. 24, but you're going to multiply that by 4. That's 96. Right, so the left-hand side is 1 plus 4 plus 18 plus 96. 23, 119. Right. The right-hand side, n equals 4. So you have 4 plus 1 factorial minus 1, because n equals 4 on the right-hand side. 4 plus 1 is 5. 5 factorial is 120 minus 1. And that's 119. Yes. So these two are equal for n equals 4, but that doesn't mean anything. Now you have to say, try it for n equals 5 or n equals 6. And if n is not even given. So how do you prove? Because there are infinitely many values for n. How would you say that this thing is always true, no matter what your choice of n is? N runs through the natural numbers, starting from n equals 1, 2, 3, 4, and so on. So often you have asked to prove formulae like this. This is a formula where you can calculate this thing very quickly by simply taking the last one, increasing it by 1, and take the factorial. You see, this was very much faster. Like if I had n equals 10 here, imagine adding 10 numbers. Then all I have to do is to say, I take 11 factorial minus 1. 11 factorial is easy to calculate. Just multiply all the numbers from 1 to 11. You subtract 1 from that. See? So All right. So these are formulae. So how do you prove formulae like this? So there is a method of proving any formula where you know the formula, right? Like in this case, you know what the formula is, and you can check the truth of the formula. Like this is what I'm doing. I'm checking the truth of the formula for n equals 4. And likewise, you have to check the truth of this thing for any value of n. And as you can see, it's good, that's going to be impossible. So there is a technique in doing this thing, and that technique is called mathematical induction. All right, and let me just tell you what induction is. It's yeah, there are 3 steps to it. Let's call it the principle. It's LE, principle of mathematical induction. Actually, the full word is mathematical induction, but they often call it just induction for short. Right? There are 3 steps here. The steps, step one is you test the formula, whatever the formula was given. For the first value of n. Now, the first value of n in this case is n equals 1. Step 2, now this is a crucial thing, which people usually have difficulty in. You make an assumption. It's called induction assumption. You will say you're not allowed to make any assumptions in mathematics, but here, it's not really an assumption. What you say is, suppose the formula is true, for some value, whatever the value is. Like we saw, the formula is true for n equals 4. Use this fact. Now it becomes a fact because you are supposing this. Use this fact to prove that the formula is true now you have to prove this. And that's, you can make that assumption and use that assumption to prove the formula is true for the next value. Now, to be a little bit more precise, my next value is, we proved it true for n equals 4, the next value is 5. So use the fact that it's true for n equals 4 to prove that it's true for n equals 5. See? Like in our case, we knew it's true for n equals 4. Right? And we want to prove for n equals 5. Now, for n equals 5, the same, we go back to this formula here. This, you see, this sum here is going to be the sum of all the way up to 4 terms. And then you add to it the very last one, the 5th term. 5 times 5 factorial. Right? So it's 1 times 1 factorial plus 2 times 2 factorial and so on. And we already knew that this is 119. So knowing that, you can substitute for this part, and 5 times 5 factorial. 5 factorial is 700, no, it's 120, and 120 times 5 is 600. That gives you 719. But then, so the left-hand side is now 719 if n equals 5. What is the right-hand side? When n equals 5, the right-hand side is, let's just write it here. The right-hand side, 5 plus 1 is 6, 6 factorial, 6 factorial minus 1. 6 factorial is 120 times 6, which is 720. And 720 minus 1 is 719. So you can use the truth of n equals 4 to prove the truth of the formula for n equals 5. But the 4, we don't have to stick to 4. We can say, instead of 4, we say k. Right? 4 was just chosen at random. So in the actual proof of this, we say it's true for some value. So we just put k, right, instead of 4, and use this fact to prove that the formula is true for k plus 1. Right. So use this fact to prove it's true for the next one. Now, once you do this, then you conclude. Step 3 is the formula is true for all n. You immediately say it's true for all values just by doing these. Right. Now, why is that so? You see, how can we make this conclusion that the formula is true for all values? So let's look at step 1 again. Step 1, for n equals 1, it's true. Right? Now here it says, if it's true for any value, it's true for the next one. It's true for 1, therefore it's true for 2. Because the second step says, if it's true for any specific value, it's true for the next one. Now it's true for this next one, so it must be true for 3. Each time it's true for something, it's true for the next one. So you keep going on like this. It's true for no end. So for every possible value, it is true. So this is the principle of mathematical induction. Very important principle. And so I'm going to prove this now. Hopefully, usually there are very, very much easier examples to prove. This particular one is quite a difficult thing to prove using mathematical induction. When this is taught, usually you give a very simple formula. But yeah, you got a rather complicated formula. It doesn't really matter. Okay, so let's prove A first. There are two parts to this, A and B. A, right, we want to use induction. So is it true for n equals 1? So that's the question, the starting point. Now the left-hand side has only got one term because it stops at n equals 1, you see. Starts at 1, finishes at 1, and it's just 1 times 1 factorial, and that is 1. See? And the right-hand side for n equals 1 is 1 plus 1, 2 factorial, minus 1. That is 2 minus 1, which is 1. So it's true for n equals 1. So this is your starting point of what we call the induction argument. Right. It is true for n equals 1. Now, the induction assumption is assume true for n equals k. For some value of n. Now, in other words, I'll put, so this is what is true. I'll put n equals k in the formula. And I say they are equal. We need to prove it's always equal, you see. So you're going to put k here. Right? R factorial, k plus 1 factorial, minus 1. Because we know that this is true for n equals k. Right? In our case, we had k equals 4, and here you had 5 factorial minus 1, which was 120 minus 1, which is 119. But generally, you don't know what this thing is. All you can say is that this is k plus 1 factorial. Now, to prove, you want to prove that this you don't know. You want to prove that this, you go up to k plus 1, right? The formula for k plus n equals k plus 1, you have to put a k plus 1 for n there. And in place of n here, you have to put k plus 1. So that gives you k plus 2 factorial minus 1. This you don't know. You only know this. Right? So how do you prove it? Well, just work on the left-hand side and try to see whether you can get to the right-hand side. Now, as we saw, this is the sum all the way up to k. It's a sum of k plus 1 numbers, starting from 1 and ending at k plus 1. So the sum of the first k numbers, k, and we're separating it from the last one. The very last one is k plus 1, and r is equal to k plus 1, and it's k plus 1 factorial here. So when you work out the left-hand side, you get the sum of the first k plus the last term, which is k plus 1 times k plus 1 factorial. Now this one here, we know by assumption, right? The sum of the first k is k plus 1 factorial. This we know is true, this part here, minus 1. And you still have to add that quantity. This is the sum of the first k, and this is the k plus 1 term. Now if you look at this, you will see that k plus 1 factorial is common. It's a common factor. This is a number. So let me take this common factor out. K plus 1 factorial goes into this 1 time, and here it goes into this k plus 1 times. I've taken out k plus 1 factorial. That minus 1 still sticks around here. Now, this k plus 1 is k plus 2. I'm going to replace this square bracket by k plus 2. The 1 plus k is k plus 2. But now this is k plus 2 is bigger than k plus 1. So this is k plus 2 times k plus 1 factorial. Now, this is a very well-known fact. 7 times 6 factorial is 7 factorial. Why? Because this is 7 times, and here is 6 times all the way up to 1. So you have all the numbers from 6 to 1 here. And if you include 7, the next one, it's then becomes 7 factorial. Right? So these are equal. So always happens. If you got this and you got this number is increased by 1 here, then the whole thing is, this part here now is k plus 2 factorial. Because this is k plus 2 times. Now this thing starts at k plus 1 times k plus 1 and keep coming right down. So this is all the numbers from 1 to k plus 2, which is by definition k plus 2 factorial. And that is exactly, we had question marks here, can you see? So we have done it. So we have used the fact that it's true for k n equals k to prove that it's true for n equals k plus 1. And therefore we can conclude that this formula is true for all possible values of n. So you can conclude that this formula is always true for any n. No, that is the proof of A. Now, there is a second part to this. B. Now the sequence is given by a rather cumbersome looking formula. Let's try to unpack this. Let's make it prettier. A1, A1, k equals 1 is 1 factorial. K equals 1, 1 squared. K equals 1 minus n. So the n, nothing happens to n, plus 1. So what do you have? You have 1. Well, 1 times anything is 1, so let's not include that 1. Here you have 1 squared plus 1, so you got 2 minus n. A1 is 2 minus 1. 2 minus n, sorry. A2, now you've got 2 factorial, which is 2. 2 squared is 4. 4 plus 1 is 5. I'm adding these two, first and last, because there's an n here, minus 2n. Okay, so this gives you 10 minus 4n. And because 2 times, let me simply expand that. A3 is 3 factorial, which is 6. Right? K is 3, so 3 squared is 9 plus 1 is 10. K is 3 minus 3n. K is 3. So this is 6 into 10 minus 3n, and you get 60 minus 18n. All right, let's just stop there for the moment, and let's work out A1. It says you need to prove this formula here. Let's work out A1 plus A2 plus A3. So we are saying that n is equal to 3. Right? We let n equal to 3. Then I am summing all the numbers from 1 to 3. And I want to show that the answer is 3. Is this equal to 3? All right. Let's add them. A1 plus A2 plus A3. What do you get? This was 2 minus n. If you add all these, 2 plus 10 is 12, plus 60 is 72, minus, and here you got minus n minus 4n, which is minus 5n, minus 5n minus 18n is minus 23n. N is equal to 3, so you get 72 minus 3 times 23 is 69. 72 minus 69. Yes, it's 3, right, as advertised. So it works for n equals 3. I unpacked this so that you will understand what this complicated thing here is. All you have to do is to substitute different values for k each time. Don't get confused. But the n still remains all the time there because you're not substituting anything for n. And only at the end, I substituted for n, and I saw that it's true. Okay, so this is much more difficult to prove using induction, that this is always true. So this is true for n equals 3. See, we just tested it out. So is it true for all n? So that's a question. Yeah, I don't think I'm going to prove it. I'll just go very quickly through the proof because all this is very time consuming. For n equals 1, you can check it out. That's easy. Your induction assumption is the following. You assume that the formula is true for n equals k. Now, you see this ak, this is sigma on the left-hand side. You're required to prove, let me say this first. Let's do this all over again. Sorry. Okay, I just want to see what you're required to prove. You're required to prove this. Now, as we saw before, this is sigma a k equals 1 to n. When you expand this, you put k equals 1, there it is. Then you put a plus sign, there it is. Then you put k equals 2, you get a2, put a plus sign, and then you put k equals 3. So you see this left-hand side can be written in shorthand like this. So you're required to prove that this is equal to n. That's what you're required to prove. RTP, required to prove. Right? So your induction assumption, oh, now you see they put K here. They should actually use R. This is making life very complicated. So, because in the induction assumption, you assume it's true for any one particular number. All right. So in this case, yeah, I'm going to assume for induction assumption that it's true for n. I'm not going to give any new name for n. So your induction assumption, we just put assumption. It's really not assumption. Shouldn't write an assumption because we're not allowed to assume anything in mathematics. Induction assumption is sigma k equals 1 to n. K equals 1 to n. And that thing there of ak is equal to n. That's your assumption. And now to prove, that when you replace n by the next one, which is n plus 1, you're going to get n plus 1. Now this is known, true, but this you don't know. You have to use that fact to prove this, right? Now we saw that sigma k equals 1 to n plus 1. We saw this before. It's just a sum of the first n plus the last one. Now the sum of the first n, by assumption, is n plus the last one. And the last one is ak plus 1. And the one that we, I'm sorry, an plus 1. And we're landing at n plus 1 there. Now I want to show that this whole thing here is equal to n plus 1. Okay? Oh. This n here is supposed to be n plus 1. And wherever the k is, I'm supposed to put n plus 1. No. Sorry, I'm sorry. Right, we know that the sum up to n is n, and I need to show that this thing here is that. Now, when you substitute n plus 1, an plus 1, you get this n plus 1 factorial k equals n plus 1. And here you have n plus 1 all squared minus n into n plus 1 plus 1. Right? N into n plus 1, k equals n plus 1. And this is n plus 1 factorial. And here you have n squared plus 2n plus 1 minus n squared minus n plus 1. N squared cancels off here, and you get n plus 2. And this is n plus 2 factorial. N plus 2 into n plus 1 factorial is n plus 2 factorial. So an plus 1, by definition, if you put k equal to n plus 1, I used this to eventually say that this is actually equal to n plus 2 factorial. All right. Okay, so that's interesting in its own right. So this is a little bit strange. All right. Actually, actually, the way to do this is you have to take the sigma of all this, you see. Let me, you have to calculate the sum of all the AKs. It's equal to, you have k factorial times k squared minus nk plus 1. Now, you're adding all these. So it's k squared times k factorial minus n k times k factorial plus k factorial. And that is equal to, you can separate these, the sum of all these terms like that. Here the n remains, you can take it out as a common factor as we saw. So it's the sum of all the k times k factorial plus the sum of all the k factorial. You can separate sum of this, sum of this, sum of this. And this part here, you see k times k factorial. This part can be simplified. It's equal to this. See? So you use the first part to prove the second part. All right, I have done this thing, and you can have a look at it. All right, let me just clear all these drawings. And we go to, see, the second part. We need to prove this. I want you to just go through this thing, because there's a lot of calculations here. That is why I was trying to avoid this. We need to prove that this is equal to, and I've replaced the k by r here. Right? It's what you call a running variable. The values of k run from 1 to n. You can give it any name, but we call it r. Right? So you got that. The reason for that is because the a part had an r in it. Now, I take this and I say you can combine these two, r squared plus 1, and put them inside there, and just leave this middle part like that, because we saw that this part here has got a formula for this. Right? In the first part, we saw that this is n plus 1 factorial minus 1, and that is what I substituted. N plus 1 factorial minus 1, but there is an n in front of this, which I seem to have missed out. There's an n here. So that's the n which is up here. And so you've got this part here is there, and here This minus n times minus 1 is plus n. So I've separated that, taken that n out, and then minus n times n plus 1 factorial is here. Right. So I need to prove that this equals n. So therefore, it's the same as saying proving that this is 0. And this is the part where I use induction for. See, if you take this part here, right, you see that I just calculate this part there, and eventually I see it's equal to that using induction assumption. Okay, it's a little bit tricky, but try to look at that and see whether you can understand it. It's one of those examples where it's difficult to prove using mathematical induction, but I've done it for you, so you can examine that. I actually forgot exactly how I did it, but you can go back and see. All right, let's now look at the next problem. After that, at least I've shown you how to handle mathematical induction. I think that is the most important thing. The actual example is a difficult one. Okay, let's now just get on to the next problem. Okay, so this is the last problem, question 15. These papers have got only 15 problems in it. So let's hope that this is not as difficult as the previous one. It's a geometry problem. Okay. So this problem says that you've got a triangle ABC inscribed in a circle. Just one moment, please. So you got ABC is a triangle inscribed in a circle, and so you got a circle which is containing A, B, and C, and you got another point chosen at the bottom here. E is chosen on this chord, and these angles here, C, E, D, is the same as that. And the problem is to determine the length of BD, given that BC over EC is 4. All right, so let's look at this. BC over EC is 4. So in other words, if this length here is A, EC, then BC is 4A. So the whole thing will be 4A. And if this is A, this is 3A. It's given. These are given. That this is 3 times that. Okay, it's also given that DE is equal to 1. DE. This length here is 1. Right, so you got DE is equal to 1, and you got this part is 3 times that. The whole thing is 4 times that, so the BE will be 3 times that. Okay, so you can see this is probably a thing which involves similar triangles, because you've got 2 angles which are the same. So let's perform a construction here to create these triangles. This DE is given, angle E is given, so it seems that I must join DC. That's a construction. I'll put that in red line, in a red line. I always put constructions in red. Okay. Now, this is, now you see you've got a circle, you've got BC is a chord, and you know every chord in a circle subtends equal angles at the circumference. So if I call this point, if I call this angle here X, and I call that angle there Y, right, these 2 angles, then you see that BC, it subtends x plus y at D. Therefore, since A is also on the circumference, the chord always subtends equal angles at the circumference on the same side of it. So this is x plus y, that is x plus y. So now, so this angle here is x plus y, this curl. Curl is equal to x plus y. But now if you look at this triangle here, this is the exterior angle. The exterior angle is x plus y. And this interior is y. So therefore, this has to be x. Right? The exterior angle theorem, because this plus this will be equal to that. And we saw that that is equal to x plus y. It's given. Okay. So now if you look at this picture, you see you got the angles of CBD. What are they? CBD are x, x plus y, and one other. And now you see the angles of CED also, angles of CED, there's an x here, and the curl, as we saw, was x plus y, are also x plus y. So therefore CBD and CED are similar. They got the same angles. I'm going to write this thing down like this. CBD is similar to, now at C, you got the obtuse angle, right? In CBD, you got the obtuse angle. And in CED, you got the same angle, C. So you can put C corresponds to C. Now at B, in CBD, you got the angle X. So you have to look for the angle X in the other triangle. In CED, the X is at D. So I have to put D there. And obviously the last one will be E. You can just check it out. CBD, D in the CBD triangle, CBD, the D is X plus Y, right? And in the CED triangle, the X plus Y was here. So it's a curve. So that's at E. I like to do this because otherwise it becomes very difficult to work out the ratios. But so once I got this, then I can write down the ratio straight away. First second over first second. CB, CD is equal to second third PD over second third DE. And then you have first third CD over first third CE. I don't have to look at the picture after that. Once I got this, then I can write this. The sides are in proportion because they correspond to these angles. Okay, now let's see now. You got BC is equal to 4a. This BC is 4a. So I can put 4a over CD here. Do I have CD? CE, yeah, CE is equal to A. So I'm going to CD over A here on this side. So CE is equal to A. And in between, you got BD, and DE is equal to 1. All right, so that's very nice now because we made these substitutions, and now we can see it's now plain algebra because you got BD. Well, let's look at these two. You got 4a over CD equals CD over A. So if you cross multiply, you got CD squared equals 4a squared. Right, which is nice because then CD is equal to 2a. So now I can put in place of CD, I can put 2a. So in the middle here, I got BD. So you got BD equal to CD is 2a over a. And that gives you 2. And that was a question. I should have said, put that on, determine the length of the chord BD. And suddenly the BD just shoots up and gives you 2. I didn't even look at the question. I simply looked at this picture here and looked at similar triangles and put them according to the ratios. But what is important is that to identify two triangles which have got the same angles, right? And there you use the segment angles in the same segment are equal. We had named them X and Y, and that allowed you to see that these two triangles have got angles X plus Y, the big one, and this one, the small baby triangle here, has got X and X plus Y also in it. So therefore, those triangles are similar, and therefore we can make the ratios, write it down in the proper way, create the ratios, make the substitutions. And that is how you tackle similar triangles. Right. Similar triangles is in your syllabus, grade 12 syllabus, grade 11 and 12, and people usually have a lot of difficulty with that. But if you use this method, that when you write the triangles as similar, put them in the correct order. See, make sure that the angles at those points are the same. When you can't just name this randomly. Once you name one, you must name the other one very carefully. Once you name that, then you don't have to look at the picture at all to get first second over first second, first third over first third, second third over second third, and you've got your ratio straight away. Okay, so that brings us to the end of question 15 and the 2025 individual team paper. All right, thank you very much for listening, and that brings us to an end. Well, let me just show you my solution to question 15, and there it is. In case you didn't follow this, you can have a look at this because it's all recorded. Okay, thank you very much. Enjoy the rest of the day or the rest of the evening.